Today we're going to talk about domain and range again, and we looked at the graphs of our functions on Friday, and today we're going to look at the equations to help us determine. But we're going to start with graphs today. And the first graph is called a linear function. And what we have graphed here is we have graphed the parent function. It's the simplest of lines with a slant. And its equation is y equals x. And does anybody recall what we said the domain of any line with a slant is from our previous notes? Well, the domain is all reals, or all real numbers. In interval notation, recall that that is negative infinity to positive infinity. And in fact, not only is the domain all reals, but the range is all reals also. And we left some space for notes here. And my notes don't have to be the same as your notes, but this is what I wrote. Any line with a slant, and make my N a little bit better, with a slant has domain and range as all real numbers. Again, I'm not a big fan of memorizing, but that might be something that's worth it. Any line with a slant has domain and range as all real numbers. We also saw a picture like this in our previous notes. This is called a quadratic function. Quadratic function. And we have graphed here the most basic of quadratic functions. We could write it in function notation as f of x equals x squared. And as we think back to our previous notes, hopefully you remember that the domain of this function is also all real. It goes from negative infinity to infinity in interval notation. But the range is not all reals. And what we talked about is we said, do we have a high point or do we have a low point in this graph? We happen to have a low point. It was close there. Try it one more time. That's our low point. And the y value of that, because range deals with the y's, its y is greater than or equal to 0. Our lowest point on that graph there is 0, 0. In interval notation, we have 0 to infinity. Because it's greater than or equal to, we have the bracket. And that's helpful to find the range, which is what I put in my notes. Again, my notes don't need to be the same as yours, but to find the range, look for a high point or a low point on the graph. To find the range, look for a high point or a low point on the graph. It's much easier to find the range with the picture. Next one. This function is a square root function. Square root function. And we have the parent function graphed. And we can write this function as f of x equals the square root of x. The difference on this one is the domain is not all real numbers. We need to look at where the picture is. And where the picture is in the first quadrant of this graph. So as I try to draw that in again a little bit, we start here. And notice that our graph is going towards the right. So when we look at the domain, our domain is x is greater than or equal to 0. And in interval notation, that is 0 to infinity. The 0 has a bracket. Infinity always has a parenthesis. Again, this picture is in the first quadrant. So all our x values are going this direction. All our y values are going up. So our range is going to be y is greater than or equal to 0. In interval notation, that is 0 to infinity again. And we're going to explore this more on the back page. So I didn't write any notes in per se yet. Is there something that you see that we could write in here? Okay. Next one. There's a variety of names for this function, but I'm going to call it a rational function. So sorry, this is a rational function. My vocab is a little bit off there, or my, I guess my pronoun, is that what an is? This is a rational function. I won't get caught up in that. And our function that we've got drawn here is y equals 1 over x. Remember, our domain goes back to the x values, and our domain is not all reals. In terms of our domain, what happens is that x does not equal 0. Do you know why it doesn't equal 0? Well, we're not allowed to have 0 in the denominator of a fraction. 1 divided by 0, it's not 0. It's not 1. We don't know what it is. So the other way we can look at this is our graph is not touching the x-axis. And our graph isn't touching the y either. So not only can our domain, x cannot be equal to 0, but our range is also that y cannot be equal to 0. And again, because we're going to explore this a little bit more on the back, I did not put any notes there. But if you can think of something, I will be glad to write it down. From what we saw in the front, it seems that there's two types of functions that we need to worry, so to speak, about. And that is a square root function and the rational function. Square root function and the rational function. And we need to worry about those, so to speak, because our domains are not all real. And we're specifically going to focus on the domains here for a remainder of our notes. And it says, what do we have to watch out for in a square root function? Well, in a square root function, we need to make sure that only positive values and 0 fall underneath the square root. We cannot take the square root of a negative number. So what we do to solve it is we're going to take x minus 6, the value underneath the radical, and we want to represent something that's positive or 0. Well, greater than or equal to 0, we'll take care of that category. And do something to emphasize that symbol right there. With the square root. Greater than 0 means positive numbers. And then we've got the equal to, there's the 0. Once we have that, then we can solve our inequality by adding 6 to both sides, and we get x is greater than or equal to 6. And I'll leave it in that notation. We'll deal with our notations here in a couple minutes. What we're looking at is using this example to figure out how to find the domain when we have square root. Our other type of function is the rational function. And what has to happen here is that we need to make sure that 0 is never in the denominator. And the denominator, by the way, is the bottom of the fraction. 0 is never in the denominator. And when we set this up, to look at an example here to illustrate this, what we do is we take the denominator, in this case, which is x plus 3, and we set it not equal to 0. Once we have the setup there, we can solve by subtracting 3 from both sides. And we get x doesn't equal -3. There's our domain. By the way, we are focusing more on the domain today. But if we would need to find the range, we would want to look at the picture. But for now, we'll use the picture to find the range, and we can practice here how to find our domain with our problems. Once again, find the domain of the following functions. Write the domains in set builder notation. What we have in example 4 here is we have 3 rational numbers. Rational expressions here, I'll say. And when we have a rational, what's allowed or not allowed to happen is that the denominator is not allowed to equal 0. So now that we know that, we're going to solve. We'll get x doesn't equal -10. You don't need to make a special line for this. Here's our set builder notation. Remember, it's for all values of x such that x doesn't equal -10. And the process is the same for these rational functions here. When we come over here, we're going to take our denominator, 3x minus 6, and set it not equal to 0. We're not allowed to have a 0 in the bottom of the fraction. So once we get it written, we're going to add 6 to both sides and get 3x doesn't equal 6. And then we're going to divide both sides by 3. So x doesn't equal 2. And finish by putting it in set notation. For all values of x such that x does not equal 2. It can be anything but 2. X is allowed to be anything but 2. So I think we're getting the hang of things. It's the same process here on C. 5x plus 2 doesn't equal 0. Subtract 2. So we have 5x is not equal to -2. And when we solve for x, we're going to divide both sides by 5. It is okay that we have a fraction. X doesn't equal -2/5. And then put it in set notation. For all values such that x does not equal -2/5. Fractions. 0 is not allowed to be in the denominator. Our other type of function, our square root function. Our square root function, remember that we can only take the square roots of positive numbers and of 0. So when we look at part A here, we're going to take our value underneath the radical symbol, the square root symbol, x minus 12 we're going to set it greater than or equal to 0. Well, we add 12 to both sides. And we get x is greater than or equal to 12. And we want to put that in interval notation. So we're going to start at 12. And there's an equal, so we're going to have a bracket. It's going to continue forever, which we can indicate with our infinity. 12 to infinity is our domain of the square root function. Same process here for our remaining two examples. What needs to happen underneath our square root is we need to be dealing with a positive value or 0. And the way that we indicate positive value or 0 is with this symbol greater than or equal to. We subtract 4 from both sides, and we get 3x is greater than or equal to negative 4. Divide both sides by 3, and we get x is greater than or equal to negative 4/3. You do not need to rewrite that as negative 1 1/3. We can leave it as the improper fraction that it is. But what we also want to write is this in interval notation. And once again, we're going to start at negative 4/3, but we're going to continue on forever after that, which we indicate with an infinity. And to finish, negative 2x plus 8 needs to be greater than or equal to 0. The value underneath the square root needs to be positive or 0. To solve this, let's subtract 8 from both sides. And the process for solving is still the same, but there is one little piece of information that we need to remember. What happens when we divide both sides of an inequality, or multiply for that matter, both sides of an inequality by negative? Well, the x is going to become positive. Negative 8 divided by negative 2 is going to become positive. But something else happens. Oscar? We have to flip this on. Greater than or equal to becomes less than or equal to. When we multiply both sides of an inequality by a negative, when we divide both sides of an inequality by a negative, the direction of our inequality symbol changes. So when we write this in interval notation, what's happening is we're going to go from negative infinity all the way over here to 2, but 2 is our last value. It's everything to the left of 2, stopping at 2.